Welcome everybody to my talk called Static Type Safety, Taking Static Type Safety to the Next Level, Physical Units for Matrices. Today we'll solve a topic that has not been solved in C++ nor in any other statically typed language before. So we'll learn how physical units from a physical units library can be used in vector and matrix types from a linear algebra library. And if you're looking for material on the topic, there's very little that comes up. So the only thing I found was this book here called Multidimensional Analysis by George W. Hart. That's actually from the 90s and fairly difficult to find. And this is the only good resource that I could find on the topic. But unfortunately, I only found out about it after I was finished with my work on the topic. But it didn't matter. I came sort of to a similar conclusion. So it helped me understand what I did a little bit in the end. So what's in it for you today? As I said, we'll mainly talk about physical units in vectors and matrices. But even if that's not interesting for you, there's a lot you can learn today about static type safety in C++ and library interface design. Furthermore, we'll also see how we can achieve the ultimate goal in library interface design, which is given by this one sentence: if it compiles, it works. Let's see how far we get. So the fun fact, if it compiles, it works, is actually something that's also being said about Rust. And the fun fact is the other talk in the parallel track right now is called Rust Features That I Want in C++. But don't worry, I won't be talking about Rust today. We will be using plain vanilla C++ and nothing else to get to the problem solution. So what do I mean when I say if it compiles, it works? During the talk, we'll follow a few design principles. First of all, we try to detect and anticipate all problematic usages and prevent them at compile time. This goes so far that it almost will feel like a built-in static analyzer that's built into your C++ compiler. So effectively, it's your math and physics teacher built into the C++ type system. On the user side, we'll try to enable sweeping changes that work once they compile again. And we'll try to make user code as expressive as possible. What does this mean? Ideally, you should be able to look at a single line of code and tell what's going on there. And last but not least, we'll see how we can achieve 100% test coverage for all compile time checks, because the main purpose of the library that I'm going to present today is sprinkling syntactic sugar on top of a linear algebra library. And there are a lot of compile time checks, so all of this has to be tested properly. Before I start with actual content, brief introduction about myself. My name is Daniel Withopf. I'm a software developer at Bosch. For those of you who don't know what Bosch is, it's one of the biggest car suppliers in the world. Bosch produces home appliances, e-bike engines. If you own a mobile phone, most likely the gyros in your mobile phone are made by Bosch. And the interesting fact about the company is that it's not a publicly listed company, so it's a private company, not for profit. So it's owned by a foundation. All the profits either stay in the company or go to the foundation and are spent on charitable causes. So as we are in Aspen today, it's a little bit similar to what the Aspen Institute does. Back to myself. So my main focus in my work was on solving real-world problems using C++. I did my PhD a while ago on computer vision and object detection in images. And more recently, I worked on I created an object tracking framework for our self-driving cars projects. And last but not least, I'm also the author and maintainer of Typeset Matrix library, which is the topic of today's talk. So during the talk, I will have a few questions for you. I would be happy if you can answer them, or even if you don't know the answer, try to answer. If you have brief questions, feel free to answer. Longer discussions would be great if you could move them to the end or offline. Before we start, a little bit terminology. So we'll be talking about physical units today. But if you don't know much about physical units, this is not a big problem. You can simply think of them as strong C++ types that behave exactly as you would expect from physical units. So you can add two quantities with a physical unit of meters. You cannot add meters to seconds. You can multiply any two physical quantities with different units. That's possible. So this is sort of enough for today's talk. If you want more background, please check out any of the excellent talks by Mateusz Pusch from CVPCon, for example. Check out P1935 that he authored and the library that's on GitHub. I also want to explain a little bit about the linear algebra terminology. So for linear algebra library, usually you have vectors. That would be anything that has a dimension of n by 1 or 1 by n, depending on whether it's a column or a row vector. There are also matrix types, of course. And in classical math, the terminology is a little bit different. There you usually have a point from a vector space. You have displacement vectors, which are the difference between 2 points, and of course also matrices. In my library, I also make that distinction between point and vector or displacement vector. These are called, or these get a vector tag. Points get a vector tag, and displacement vectors get a delta vector tag. So whenever I'll be talking about displacement vectors or delta vectors, this will be a proper vector in the mathematical sense. And of course, there are also different matrix types in the library. We will see later which different types we have. Good, moving on to the actual task. We want to combine a linear algebra library with physical units. For physical units, as I already mentioned, there's P1935. For linear algebra, there's, for example, Eigen or P1385, proposal for the standard library. Bob is actually in the audience today, welcome. And Guy Davidson is the second author. So, brief example of how we can use these two libraries. So the first line of code creates a quantity with a dimension of length dimension and a physical unit of meters. The second line creates a vector with 3 entries and a scalar type of double. Now, first question for you. Does anybody have an idea what we could do as a simple thing if we want to try to combine the two libraries? So if we want to use physical unit inside a vector, simplest thing that you can think of?
So you can attach the unit to the whole vector?
Yes, I'm going to attach the unit to the whole vector. And do you have an idea how that could be achieved?
Well, it'd be the unit length of the vector for the direction and impact that you're wanting to take it, or that it would be displacing an object. And so it's, when you put a meter on it, it would be how many meters long your vector is and on what dimensions, right?
Yeah. Bob?
As I recall, the idea was that the data type, in this case double, would be replaced by a type which contained both the units, like meters, as well as the scalar quantity.
Yeah, exactly. So Bob gave the answer. So you simply replace the value type inside that vector with your physical unit. So really simple. That's the first thing that usually comes to people's minds. And it also works for these small examples here. So here we have two vectors, v and u. And you can add these two vectors together if they have the same physical unit as a value type. You cannot add them together if they have different physical units or different value types. So this is the simplest solution. Yes, question?
What about the reverse of this, in which you plug in FS vectors double inside the...
The question was, could we do the reverse, like plug in an FS vector into as a value type into the physical units library? I think Mateusz actually has both examples in his library. I would consider this here a little bit better, but in the end, we'll soon see why both approaches cannot solve the whole thing. So we'll get to that. But the other way around might also be possible. For me, this here is a little bit more intuitive, I think. Good, let's move on to a slightly more complex example. So let's assume we want to track a vehicle in one dimension. If we want to do that, we would need a state vector with a distance in meters, velocity in meters per second, and acceleration in meters per second square. So let's just create a 3-dimensional vector like is shown here. We input 1 meter, 2 meters per second, and 3 meters per second square as an initializer. And then we put that in our vector, but wait, which scalar type or which value type should we use here? No longer possible. So
it's not a vector, it's a tuple.
Well,
you already answered the next question. Fedor, he said that's not a vector, it's a tuple. So my question would be, which C++ data type can you use to represent this? Fedor?
Sorry, it's a tuple.
No, perfect. Yeah. It's the tuple to the rescue. Yeah, that's the next idea that you usually have. And I actually talked with Zach Lane earlier today. He contacted me and he wrote a library 10 years ago or so where he tried to do something similar. we will see in the following that this can work, but it also hits a dead end pretty soon. So let's see. We're moving on. We had vectors. Now let's move on to matrices. Let's see what the unit structure in a matrix looks like. So here we have a 4x4 matrix, and this means we can have up to 16 different physical units types in such a matrix, potentially. And this is a fairly small matrix. So we could have 10x10, 20x20 matrices, up to 400 different elements. So not sure, do you really want to put that in a tuple and live with the compile times? Probably not, because it gets fairly, like compile times will explode, I guess.
Then variant?
Variant, yeah, might be the next option. We'll see what the right solution is. So I think it's fairly obvious that tuple is probably not the solution, especially not for big ones. So for small examples, yeah, you can get it working with tuples. That's no problem. Fortunately, that's also a result from the book. The unit structure in matrices is simpler than this. So it's not, you don't have 16 completely independent entries in your 4x4 matrix. You have 4 row units and 4 column units. And if you have this, then all the units in the individual elements are simply a combination by the respective row unit and the respective column units. So you either multiply them, or we'll see later, well, it's an operation. So you do an operation between row unit and column unit, and this is the full unit structure in all physically meaningful matrices. So it's not proven in the book, it's a claim by him, but I'm also pretty sure that all matrices I've occurred and what I could come up with have this structure, so I'm fairly certain that this is true. Question?
I guess this is valid if you're using matrices only in the context of matrix vector multiplication, like in linear algebra, right? If you have a general array for other purposes.
Yeah, if you, the answer was,
16 units.
yeah, if you, the answer was if you have a general purpose array, then it might be different. Yeah, so we're mainly talking about linear algebra. Yeah, if you have anything else in mind, talk to me afterwards. Good, now let's see how can we access an element in such a matrix. Well, we simply use the function call operator and access the element at index 4 and 2. So row index 4, column index 2. Can this work? One answer was sure.
Well, sure, it can work.
What would be the return type?
Whatever the unit is of that.
Yeah, whatever. So the answer was the return type would be whatever the unit is of that entry. But these are runtime indices. So we could return a variant, but again, just because we have that type doesn't mean it's a good idea to do that. So what we can do here is something like this. So we have a compile time data type that you can, in which you can store the indices, or you have a named method like this here, coefficient si, that gets a non-type template argument, and you specify the 2 integer indices.
For this general example, the 2x4 index, your matrix is compile time typed for the type of unit that's in there, correct? So you just can't deduce it off of from what the matrix type was or what the element was?
The question was, the information is available at compile time because we tag it. If this could be deduced from the matrix type, well, it can be deduced in the last 2 examples, but in the first one where it's a runtime index, yeah, no way. At runtime, you can't say what the return type should be. You always need it at compile time.
The elements don't have the same unit type?
No. The answer was if all of the elements do have the same unit type. No, that's actually the whole purpose of my library. Non-uniform. I'm working with non-uniform or potentially non-uniform units in the matrix. So if you have uniform ones, then all bets are off. Use the simple solutions. They're probably going to work. Yeah. This is mainly concerned with having non-uniform units.
I'm not sure, but I think what confuses people is that since they are compiled and constant in your example, then there might be if concepts or ways to have different types.
No, with compile time constants, that's his point he's deducing.
Yes, but 4 and 2 in the first one is the concept per. So you can do everything concept per and in principle look at all the cases. I mean, I'm just...
Yeah, the question was whether this could be const expr, the first one. But yeah, you also want to support runtime indices if you have an interface like this, so no. And we'll get to that. I have a different solution for that. Because is this really expressive code? I mean, if you have a three-dimensional vector, then maybe use your integer indices. If you have a 10 by 10 vector that stores positions, velocity, accelerations, or maybe it's x position, x velocity, x acceleration, I wouldn't want to write code or have to read code like that. So that's actually also part of why I wrote the library. And we'll see on the next slide. So now we'll move back to classical linear algebra libraries, because that's where my activities on the topic started. So I started to look at code like this. So you access, for example, other vector at index 3 and assign it to measurement vector at position 2. Now, when you see a code line like this, can you tell what this is doing? It's fairly difficult because you have no idea what the indices actually describe. So two questions here. First of all, what do the vector entries describe? And second of all, is this an out-of-bounds access? This could also be an out-of-bounds access. Now, second try, maybe. The author improved this a little bit and uses, I don't know, enumerator constants for the indices and accesses other vector at position x index and assigns it to measurement vector at velocity x index. Now, when I see that code, I again have two questions. First of all, have the right index constants been used for that vector matrix? Because we don't have a guarantee that these index constants are actually meant for these vectors, at least not if you use plain vanilla libraries. Of course, you could write an extension that does this. That's possible. And the second question is whether assigning a position to a velocity is really intended. Most likely, this is a bug, because I guess your physics teacher would agree with me, you shouldn't assign a position to a velocity. And then maybe in the last try, the code line looks like this here. We access other vector at velocity x index and assign it to measurement vector at velocity x index. Now this looks okay, but still there's one question remaining. Namely, in which coordinate frame are the two vectors? Because if the one is from one coordinate frame, the other one from a different coordinate frame, then again, this could be or is most likely an invalid operations if the two coordinate frames do not overlap. So,
or a conversion has to be taking place under covers.
Yeah, the comment was, or a conversion would have to take place undercover. But again, there in my library, I try to not do anything underneath the covers. Most of what is happening is explicit, so I didn't want to hide anything underneath.
So what you're saying is that you want to solve the problem with units, but also the problem of point of reference or origin.
Yeah, the comment was whether I want to solve the physical units problem, and also the question of how to annotate the vectors with different things. And exactly, you did the introduction sort of for my next slide. From that, I came up with a linear algebra library wish list. So what I want ideally from my linear algebra library, maybe not from a general purpose linear algebra library, but for one in our application, is a protection against out-of-bounds access at compile time, meaning it should not be possible to access anything out of bounds. I would like to get expressive and enforced names for all vector and matrix entries. I would like to have support for non-uniform physical units in vectors and matrices. That was the comment earlier. And I would also like to have a physical unit checks for all matrix operations, again at compile time. And we will see later that we can actually achieve much more than just a plain physical units check. Yeah, Bob?
I have a question for you about the non-uniform nature of the units in the matrix.
Yeah.
Is it the case that if you look at the matrix in your example of a 4x4 matrix, well, 4x4 matrix, is it the case that if you looked at the types of what would be in each element of that matrix matrix is symmetric about the diagonal in terms of its types?
The question was, when we looked at the matrix from the beginning, the 4x4 matrix, whether the units are symmetric around the diagonal. For a covariance matrix, this would usually be the case, but you can also have like a smaller block of a covariance matrix where this is not the case. And we will see later how I'm tagging this, so we will have that information available soon. Last but not least, as we mentioned, I also want to have a coordinate frame annotation for vectors, matrices, and transformations. I think actually Chris Ryan gave a talk a while ago about geometry, an introduction talk at CppCon. Yeah, where he also mentioned like different coordinate frames for the 3D graphics. This is something that you could solve with this. If you have different like crops of an image, you could tag that statically in the type system, so there's no way you can misplace these two or do incorrect operations. Good. So this was the first part of my talk, where we talked about the motivation and saw how simple a simple solution would look like. And now I want to move on to the solution space, how I solved it in my library. The first ingredient that we're going to need to identify the entries in a vector matrix are what I call named index structs. These are simply empty structs with a certain name. So in this case, the DXC stands for distance x Cartesian. And this is such a struct is created by deriving from a base class that has 3 template arguments. So you specify in which coordinate frame this is. This is a vehicle front axle coordinate frame in this example. You could pick any names and any frames that you can create. We specify that this is the x-axis in this frame. And we specify the physical unit, that this has a physical unit of meters. On the bottom, you can also see how you can create these coordinate frames. You simply derive from a base class in my library, and you specify whether that frame is moving or not moving. This will be interesting for later when we transform between frames. Now we could also create a different index struct for, this is here the distance y, so the y position in a sensor frame, so in a different frame. And as a general rule, how I construct these index names, there are 3 parts of the name. So the first part is the physical quantity, distance, velocity, acceleration. Second part is the axis, x, y, z axis. And the last part is the coordinate frame. Now, if you paid close attention, you might have noticed that DXC does not contain a mention of the coordinate frame. I did that because the vehicle front axle coordinate was the sort of standard frame in our application. And as you have to type that fairly often, I left out the name there. So that's a convention for the users. But anything in here is completely configurable. So if you want different names, if you do not want macro case, different casing, the user can decide on what the names should be. Ideally, they should be speaking names so that you immediately see which frame is it, and is it distance, velocity, acceleration. That's the main criteria. Question?
Yes, the SI meter is from MP units?
The question was whether SI meter is from MP units. Yes and no. So we have an in-house linear physical units library in use for over 15 years now. So usually we use that, but I also have a binding for MP units. So both work. No.
What about like mass or something that doesn't have direction?
Sorry, what was it?
Like, if I have, let's say, mass.
The question was if you have mass that doesn't have a direction. Yeah, then I will later show you can also create non-Cartesian indices. That's a different base class that you have to use. We'll get to that, but a few slides later. So let's see what's inside the library. So this is the first type that we need from the library. And it's called, as the library itself, Typeset Matrix. And you have 4 different template arguments. First template argument is the scalar type. So do we want to store doubles, floats, integers? Second one is a type list of row index types. So these index types we've seen before. Second argument are column index types. And the last argument is a matrix tag that is used to distinguish the different types of vectors and matrices. I will later show what the full taxonomy is here. There are a lot of types, so you can have vectors, displacement vectors, transposed versions, information vectors, covariance matrices, Jacobians, and a few more. Now, the only data member in this class is an eigenmatrix in this case. You could use other libraries, of course. And the eigenmatrix gets the same scalar type as Typeset Matrix, and we use the size of the row index list and the column index list to specify the dimension of the matrix. Question?
Yeah, so this obviously shows a statically sized matrix. Do you also have some mechanisms that at least partly support dynamically sized matrices?
Question was whether I support dynamically matrices also. Currently not. You could use a vector of these individual elements. The dynamically sized version would also work, but only if the dynamic dimension does not influence your physical units.
Yeah.
Then you can do that.
Like, rows of observations with.
So in our application, we don't use heaps, which is why I removed the dynamically version, or I did not implement it yet, but of course this is possible. Then we have a few aliases here. This is a typesafe vector, simply a typesafe matrix. with a given row index list. And as column index list, I specified just a list with one index and no index type. This is sort of an indicator that this index does not influence the physical unit. And I also forward the matrix tag that is passed to that alias. And now we can create the first type here. So this would also be an alias, a position vector in the vehicle frame. This is a typesafe vector with a given scalar type and a three-dimensional type list with a dx, dy, and dz I mentioned in the beginning. And it gets a vector tag, so this would be a point in the mathematical sense. Now let's see how we can create a vector and access its element or its elements. So here we create such a position vector with a dimension of 3, and we now list the individual elements, the 3 elements. For that, there are 3 different versions listed in decreasing order of type safety. So this is the 3-star typesafe version, where you call the entry method and specify an index that's contained in another position vector. So this would extract the dx index from other position and then assign it to the dx index in the current vector that we're constructing. There's a full check that dx is part of other position, that dx is the first index in the vector we're creating, and if any of this wouldn't be true, then you get a static assertion. Second, little bit less type-safe option is to use rep coefficient si, specify the index dy in this example, and then pass a physical unit to that method. So here we only have a physical unit type safety in this example, so there's a check that the unit matches up and that dy is actually the second entry of the vector. And last but not least, the least type-safe version is to use rep coefficient. There you simply pass a scalar. And there's no physical unit check, so this method should be avoided as much as possible. Maybe if you want to set a 0 or 1, then it makes sense, but otherwise, this is usually a code smell. Now, when we want to assign, read or write from a vector or matrix, we can do the same thing. The first example, again, is the most type-safe one. So there we have a full check that so we call the entry method on other position and then assign entry on the one we want to assign to. And there's a full check, again, that dx is part of other position vector and that it's also part of position vehicle that we're assigning to. If any of this would be untrue, the user gets a static assertion. Second version that's a little bit less type-safe is to use coefficient si method for reading and coefficient si ref for writing. So here there's only a physical unit check, so it's possible to assign dy, the y position index in one frame, to the x position index in a different frame. And I should also mention why these are 2 methods, maybe you noticed. So the left one on the left-hand side returns a proxy type with overloaded assignment operator because we're not actually storing physical units inside the vector or matrix. We're giving the impression to the user that it's part of the matrix so that we can have all the optimizations of the underlying linear algebra library available. And again, least type-safe version is to use the add method. Here we can assign the y velocity in sensor frame to the x position in vehicle frame. So again, very questionable. This operation should be avoided if possible. Good, there are more ways to create a vector or matrix. This here creates a 3-dimensional displacement vector, and we can initialize the first 2 elements by creating taking the first 2 elements from other velocity sensor by calling that head method and multiplying it with a duration in seconds. So duration in seconds multiplied with a velocity gives you a displacement vector. And that displacement vector can be used to initialize the first 2 elements of our 3-dimensional vector. And then again, we list the last element by calling the entry method. Then, of course, this can also be taken to 2 dimensions. So you can also have a type-safe matrix. Here, this is a covariance matrix that contains x position and x velocity. And then you list, for example, 4 individual elements by calling rep coefficient si. And you now need 2 template arguments. So as it's a matrix, you need row and column index. Of course, you can also use the other methods that I mentioned earlier. What you could also do is to create a matrix from 4 or n columns, from 4 rows, from 4 smaller blocks, or from 3 rows and 3 smaller blocks in the last row. This is also possible. Now, I'm happy that this is the first talk where I actually see faces when I'm at that slide, because this is usually the point where I ask or want to see if people think that this is an easy interface or if they think that this is verbose. So I guess you think it's verbose, but do you have an idea why this might be a good idea, always having to list the indices? Or what this enables in the end?
I don't understand completely, but maybe I just made something. So what you want to do is to kind of forget the order of the vector or the tuples or even the arrays, and then do the abstraction on some kind of units and coordinate system. So you can have two vectors in two different, let's say, in two different coordinate systems, but x and y are swapped in one of the vectors, and still you can assign between the two.
Yeah, the question was whether the idea is that I have like x and y position in one vector and the other one contains y and x position, and you can just assign them. That would be one option how you could implement the library interface. Actually, for that purpose, I have a special method that has a special name, because I think this is not something that should, again, happen under the hood. This is something that the user should request. So what's that for here is that we can enable all the compile time checks. So here I can now check that the user has listed all elements, that he has listed all elements in the correct order, and all of this is checked at compile time. So meaning, if somebody wants to, so if you want to change the order of the indices in your vector or matrix, the only thing you have to do is go find all the compiler errors. The compiler will scream at you, and once you've fixed all your compiler error, the thing will work again and you won't have any bugs left over. Because this is checked by the library, so I always know what the order is supposed to be of the entries in my vector or matrix. I can check this, and if it's not true, the user gets a static assertion, and this is sort of, this enables what I mentioned earlier. If it compiles, it works. So of course, this is a little bit verbose, having to mention these indexes always, but at least in our application, I found that very helpful, because otherwise you would always, like, you have to do a lot of code reviews, and if you don't know what's in the indices of a vector, then it's very difficult to do a code review if you don't know the code, like everything of the code.
Yeah, I understand the necessity of this if you're going to put raw numbers in the ... But if you delegate that responsibility to the units library for scalars, then you don't need to do this. You just need to check.
The question was whether we can delegate the responsibility for checking whether the unit matches to the physical units library. Well, there's a unit check. You could, of course,
delegate how to construct these coefficients.
How to construct
the units. Right?
Yeah, but here I'm not just delegating the construction of the physical units. I'm sort of I want to identify each entry with the information. Where does it belong? What does this thing actually describe? Yeah. Good.
Could you go back for a moment? Which of these, I mean, some of them kind of repeat accidentally, but which of them are redundant?
The question is if anything is
coupled,
anything is redundant. Yeah, the first one is the row index. The first index in the first row is identical because this is the first row. So it's sort of redundant, but yeah, it's difficult to come up with an interface where you only mention that once.
Basically, in other words, like if I wanted to change one of these types, how like I would have to change them consistently in multiple places here, right?
Yeah, the question was when you change the name, you have to change it in multiple places. Yeah,
Could
that's
you
true.
set up a
Okay.
using outside of this, and then just say using, whatever that using name was?
Yeah, but it would still be
Okay, sorry for interrupting, but I think we have to speed up a little. It's because I have 90 minutes material. So let's see how we can access a matrix element in a vector matrix. So here on the left-hand side, we create a Jacobian matrix, and that's visualized on the right-hand side. So that Jacobian contains a measurement, dr, that's radial distance in units of meters, radial velocity, vr, with unit meters per second, and an angle. That could be measurements from a radar sensor, for example, that tracks another vehicle. The columns describe x, y, and z position in vehicle frame. And now the question for you is, what should be returned, what physical unit should be returned when we access this element here? So we're accessing the element with where the row describes the radial velocity with a unit of meters per second, and the column describes the y position with unit meters. And we're in a Jacobian matrix. Does anybody have an idea?
Square per second?
The answer was meter square per second, almost. The idea is almost correct. So you multiplied the two units. Another try.
The alternate would be to divide.
The alternative would be to divide, which gives us
Inverse seconds.
1 divided by second, exactly. And if we introduce the notion of a row exponent and a column exponent for these matrices, then we can generalize that to all different types of matrices. So a Jacobian matrix has a row exponent of 1 and a column exponent of -1. And then the general rule for the physical unit is take the row unit to the power of the row exponent, 1, multiply that with a column unit raised to the power of the column exponent, -1 in this example, which would mean we divide meters per second by meters and end up with 1 divided by second.
But you're saying that this is a property of the Jacobians?
Yes, I'm saying that this is a property of Jacobians. So for all Jacobians, this is how you get to the units. For covariance matrices, it's multiplication, so they have 1 and 1 as exponent. We'll later see the full taxonomy.
Because Jacobians are only applied to differentials in some sense.
Yeah, Jacobians are sort of, you take the derivative, a Jacobian describes the derivative of, in this case, the row with respect to the column. So this is a nice semantic annotation so that you know what's actually happening in your code. Good, this is the full taxonomy of all vector and matrix types. So here on the top we have covariance matrix, both exponents are 1, Jacobian that we've seen. There are information matrices which have both row and column exponent -1. We've seen position vectors, displacement vectors, and an information vector. And the last block are what I call vector collections. So these are matrices which contain individual vectors as columns or rows. And there's again position vector collection, displacement vector collection, and information vector collection. And of course, you can also take the transpose of each of these types. I didn't list them here, it should be obvious what the exponents are. Good. Until now, we've achieved unit-safe element access and out-of-bounds protection. Now the question is, can we maybe achieve even more than this? Let's see. So first of all, let's try to be unit-safe for all operations. Again, a question for you. Should this operation here be allowed? So we have two vectors. The vector on the left-hand side describes x and y position in vehicle frame with a unit of meters. And the right-hand side describes a velocity vector x and y with unit meters per second. Should this addition be allowed?
No.
Answer is no, of course. The physical units don't match up. There's no way that this is correct. Next example. Should this be allowed here? So on the left-hand side, we have a vector where the left-hand side vector contains meters and meters. So it's a position vector. And the right-hand side is a displacement vector, also with a physical unit of meter. Should this operation be allowed?
Yes.
Answer was yes by Chris. Not that simple. That was a trick question.
Is delta Laplacian?
Delta stands for delta displacement vector, what I had earlier. So nothing with Laplacian, yeah. So because I said it depends, so the answer is correct in some cases that this should be allowed. But what if this describes x and y position and y and z position in the same frame? Then these vectors describe completely different things and they should not be added together. So the reason why this should not be valid is because the index types do not match up. So the lesson that we should take home from this slide is that unit safety is not enough. We actually need index type safety. Because the physical units could be identical, but it could still describe different things.
Because you don't want automatically to upgrade. You could go into 3D space and create a vector. You don't want to.
Why would I? The question was whether I could automatically upgrade to 3D. Why would I want to? Well, of course you can do that if you do everything magically, but yeah. I don't think this is a good idea because the user would have no idea what's happening there. So my design principle for that library was, you should always see what's going on. I'm not sure who was next. Michael, maybe?
No.
Okay.
I was going to ask, for index type safety, you have achieved semantic safety, but that's actually not true because the index has more meaning than just semantic.
Yeah, the question, or comment was that I have achieved semantic safety, and yeah, index safety might even be more than this. Yeah.
I was going to ask or point out, in that last example, I don't like your index type safety name. I'm maybe
Yeah.
not understand what you're using. I would say the first matrix is, in this case, it's a matrix XY, and the next one's a matrix YZ. They are incompatible. They would not add.
Okay.
But to just call it, to
Yeah.
specify via that it's an index
Yeah.
misset.
Okay, the comment was that the
It's matrix itself, not the elements.
index type safety might not be the best name. I'm open to any new names.
Well,
No
it's
problem.
more like a map. Right?
Yeah.
Parameters
map.
and types.
Yeah,
And if
so in
this
the
is a 3D coordinate, you actually have an implied 0 for the other coordinate then, right? Yes? No?
well,
Because you wouldn't mix them if they...
the question would be if this were 3D. Well, they aren't 3D types. It's a two-dimensional vectors. Yeah.
Right.
So, okay, as I mentioned, we have to speed up a little bit. This is a nice example from the slogan from the beginning, in my opinion. So if it compiles, it works. Now let's see how more complex operation looks like in the library. So here we're multiplying 3 matrices. So on the left-hand side, we have a Jacobian, in the middle, a covariance in vehicle frame, and on the right-hand side, a transposed Jacobian, which is usually how you get to a different frame for a covariance matrix. Now what happens inside the library when we do this multiplication is that we check that the indices in the orange boxes here are identical and that the row and column exponents are the sign inverse of each other. It's a little bit similar to classical linear algebra multiplication where you check that the inner dimensions match up. And if this is the case, then these inner indices cancel out and we move the column indices from the right-hand side over to the covariance in the middle, or the matrix library does it. Then the same thing is done on the left-hand side. We check that the indices match up. We check or verify that the exponents are the sign inverse of each other. And if this is the case, we move the row indices to the middle. And now we sort of transform that covariance to a different frame. We now have indices in sensor frame as rows and also indices in sensor frame as columns. And this is exactly what we assign it to here on the left-hand side of the equation. So this is a valid operation.
So that was just a shortcut that you were demonstrating, or if you had actually gone and multiplied out each of those with the identities, it would have reduced
The question
units correctly.
Was whether this is just a shortcut or whether when I multiply everything out, then I would have come to the same result. So yeah, that's true. If you multiply everything out, you would get to the same result.
Okay, so
But this is sort of the structure. Yeah, it makes the library much easier. And if you would use the tuple approach we had in the beginning, the only way you have is actually what you mentioned, that you multiply it out by hand. But I don't have to do that because this is the real property of the real taxonomy of the problem. Good. Now these are the classes that are part of my library, the 3 most important classes. So we have a typesafe matrix, we've already seen that. And then this inherits from a matrix base class with a CRTP pattern. And the third building block that we need is a matrix expression similar to normal linear algebra libraries. Such a matrix expression gets 2 template arguments. The first one is a promotion type that's just responsible for inferring the resulting type inside my typesafe matrix library. So this is sort of the syntactic sugar promotion. And the second argument is an expression from the underlying linear algebra that we're using, maybe eigen in our example, which is responsible for doing the calculations at runtime. So 2 parts. One is the compile time information, the other one the runtime information. Now I want to show what one of the operators in my library looks like, or the checks that are done in the operator. So here we use as a return type, we return the matrix expression that I showed earlier. We use the promotion 2D addition as the first template argument for that expression, and this is responsible for inferring the return type. The second argument, so what should be done at runtime, this is simply the deckel type of adding the 2 underlying types. So if you have eigen underneath, you add the 2 eigenvectors or matrices or expressions that you have stored, and this is what happens at runtime. Now I want to show what this promotion 2D addition looks like. So this inherits from a few base classes, and otherwise the class is empty. So it inherits from requires identical scalar type, and that base class does exactly what the name says. It requires that the scalar types are identical between expression 1 and 2. Furthermore, it also injects the scalar type of the result into this promotion. Then we inherit from 2 more base classes. These require that we have identical row and column indices in the 2 arguments. Then we also require that the row and column exponents are identical, and last but not least, we require that the matrix tags are addition compatible. That's what I mentioned earlier. You can add a point to a displacement vector, but you cannot add 2 points. If you have 2 points in a mathematical sense, an addition is an invalid operation. And this is what's being checked by this requires matrix tags, addition compatible. Now, last step, let's look inside that requires identical row indices class. This is an almost empty class that just contains 1 static assertion. And that calls a type identity checker that checks whether the 2 row index lists of the 2 arguments are identical. And as I said, we inject the resulting row index list in that class and also in the derived classes then. Now let's see what this means for compiler error messages. So if we add a 3-dimensional vector and a 2-dimensional vector together, then we first of all get a static assertion from the type identity checker we've seen before that alerts you that something's wrong, 2 types are not matching. Then we continue in the instantiation history, and we'll see that promotion to the addition caused that assertion. We will see that this instantiated requires identical row indices, so the row indices did not match up. And last but not least, we'll end up in the type identity checker template and see, okay, one type list has 3 elements, the other one 2, they don't match up. The same thing would of course also happen if you have 2 2-dimensional type lists that have different indices, then they also wouldn't match up. Now, we're not in C++11 anymore, so I should mention the library has been designed for C++11. We are in 2020 by now, so we have concepts. So this is an example of what the error message would look like if you use concepts here. So I converted it to a concept edible. In general, I think the recommendation is to not use concepts for a single operation. Yeah, I'm not sure, it might be a little bit different for my library. So you see that you again get really nice error messages, or maybe even better ones with C++20 concepts. And you've also formalized it in the language, what you're doing here. What I did on the previous slide mainly works for conjunctions. If you have disjunctions, that would break down. So concepts are much more powerful here. Good, now I mentioned we also want to do compile fail tests. So we want to test that, well, the main property of the library, or one of the main properties is that it catches the errors with static assertions. So we should test that. And this can be done with a simple CMake trick. So you add an executable fail test here. Then you exclude that from the default build in the next line. You add one define with target compile definitions. That's called fail test 1. And then we add a test, and that test does not run an executable. It calls out to CMake build. So the test is actually calling CMake build with our define set. And then we grab the output of that command to see or to verify whether a static assertion has been emitted by that test. And then we can write a small test here. So you use that fail test define, fail test 1 here, put it inside an if-def. And here we have a line of code that should not compile. So we're adding 2 vectors in the line here. And 2 vectors, as I mentioned, to point in the mathematical sense, cannot be added together. So this is an invalid operation. It produces a static assertion. And this is actually checked with that small trick here. As you might see from the title of my talk, this is what I call compile fail testing Stone Age, pre-C++20. With C++20, there's a nice trick that can be used to make that much more prettier. This is something that I actually got from Mateusz Pusch, who listened in to when I gave the talk the first time, though credits go out to him for pointing me to this. So what you can do, you create a concept, valid addition, that uses a requires expression with a nested required expression and an ad hoc constraint in there, and that simply specifies that the addition, so adding the 2 arguments, should be valid. I hope I got the terminology right here. And when we do that, then we can create our two matrices, for example. Here I'm doing a sanity check beforehand, so I'm actually executing a valid operation. So I'm adding a vector and a displacement vector, and this should not fail. So this should be a valid addition. And now I can do the first compile fail test, where I'm checking that this valid addition concept is false when I add two vectors, so 2 points in the mathematical sense, then this should fail. And maybe we want to do a second check. If we add a 3-dimensional vector to a 2-dimensional displacement vector, this should all be also fail. Now, the big difference here is what I had to do before. I had to run the compiler 1,000 times for 1,000 tests, which is really tedious and takes up a lot of time. Here, you simply have one file that gets compiled once, all the checks are executed, and you're finished. So this is really, really big improvement to what I had before. Yeah, question? The question was, or the comment, this could have been done with Withopf tricks before. Yes, it could have been done, but I think I listened to a talk that also described that a while ago. But I think in this case, you're not testing the actual interface. You're testing sort of the types that are used as constraints on the interface. So what I wanted to do or wanted to achieve, I actually want to execute the operation. And I think with that concept trick, you're sort of executing the operation, or the check is done in the same way. So you're checking the real thing and not something that might be used underneath, where you have to make sure that it's the correct thing. Yeah. Next question.
Not just Withopf, but with any spinning trick, you can do that. Like, for example, you can put that entire expression in a decal type, trailing return type that you have now in your concept.
Yeah, the comment was that could have also be done with a decal type expression. Yeah, maybe we can talk about that offline. Would be interesting. The question is always, does it actually test the actual interface, or does it check something that's related but not identical? Yeah, Ben?
Why do you require the nested requires expression?
Why do I?
Just to require the expression.
The question is, why does it require the nested requires expression? Honestly, I don't know. Yeah. I'm not that much into concepts yet because I wasn't able to use it yet. We're still stuck at pre-C++ 20, so I took that from Mateusz, so yeah.
I'm not sure on this, but I believe that it's because you're creating a new concept that is A requires that contains a requires. So they're kind of, since they're one inside the other, then it becomes compound.
Yeah.
So it's a double require.
Comment was that it might be because it's they're nested, and that's the reason why it's required. Yeah, yeah. Okay, I can't answer it, so yeah. Let's move on, maybe. So, okay, this was sort of the lowest details of the library. Now I want to take a step back and take a look at the big picture, what we've actually achieved so far. So I want to compare what we had in the beginning, the uniform matrix approach, where we use the value type of a vector to represent uniform matrices, versus a type-safe matrix. So here on the right-hand side, this is actually taken from the book that I mentioned by George W. Hart, and it shows the classes of physical unit-aware matrices. So that uniform matrix approach with a value type can represent the gray area here in the middle, which is fairly small compared to what I'm trying to do with type-safe matrix, which is to model the second outermost oval in blue. And we can see this is a much bigger problem class. And we will now also see that even inside this gray area, type-safe matrix can model the problem in much more detail and prevent a lot of operations that are actually invalid, but that would be valid with the other approach. To see that, let's compare what can be added and multiply with the two approaches. So on the left-hand side, the unit as value type approach. And here in the table, we'll add two vectors A and B. And the different options that we have is an xy point or position vector. We have yz position vector, an xy displacement vector, and an xy velocity vector. And as we can see already here from the yes and no's in the table, most of the operations are valid, even if you mix up like the indices, if you add two position vectors. And the only thing that can be prevented with that approach is the last column, where we mix up the physical units. I mean, it's also natural because the only annotation that we have available are the physical units, so of course it can't prevent anything else. For type-safe matrix, the situation looks a lot different. So for example, we cannot add two points in the mathematical sense, even if the indices are identical. We can also not add two types with different indices. What we can add is a point to a displacement vector if the indices are identical, or two displacement vectors with identical indices. Now, moving on to multiplication. When we multiply two matrices A and B, here we again have the different options. So we have a Jacobian, Jacobian transposed, covariance, and a vector. When you multiply these, you can now see that all of the operations are valid with that approach. Of course, given that the dimensions match up, that's the precondition. But if this is the case, then all of these operations are correct, which is again fairly natural. We don't have an annotation, whether it's a Jacobian or covariance or a vector. So yeah, not much we can do here. With type-safe matrix, the solution looks a lot different now. Most of the table turns to gray because these are invalid operations that don't make mathematical sense. So what we can multiply are two Jacobians, and I put a maybe here because they can be multiplied only if the indices match up. We've seen that earlier in the multiplication example. You can add a Jacobian on the left-hand side and a covariance on the right-hand side. You can, multiply. You can multiply Jacobian with a vector, two Jacobian transposed, or a covariance with a Jacobian on the right-hand side. So I hope this gave a good impression that, as I mentioned, first of all, the problem domain space is much bigger with type-safe matrix, and even inside the gray area, so the part that both approaches can model, we get much more detail, much more fine-grained representation of the problem domain, and we can prevent a lot of operations that are invalid because we have the semantic annotation for all of that. Good. Now we can also represent transformation and rotation matrices in the library. This is an example of an isometry with 4 different template arguments. First one is scalar type. This is the destination frame, so to which frame the isometry transforms. Source frame, from which frame the origin is or from which frame we are transforming to the other frame. And last but not least, the dimension. This then enables automatic compile time checks for the correctness of our transformation order. So we can apply that transform from ODOM to vehicle frame to a position vector in ODOM frame, and we get a position vector in vehicle frame on the left-hand side. All of this is checked by the library inside the type system. So if any of the types would be different, this would not work, and you get a static assertion. Now, moving on to the next example, again a question for the audience. Should this be valid or not here? So we have a full isometry. I should mention isometry consists of rotation plus transformation. We apply it to a velocity vector in ODOM frame, and we want to assign it to a velocity vector in vehicle frame. Should this operation be allowed, or is that valid? What do you think? Answer was yes. So I want to repeat that the transformation consists of a rotation and a translation. So should we translate, like enlarge or shrink the velocity vector if we move to a different frame? No, we shouldn't. So this means this is an invalid operation and is prevented by the library, because the velocity is only rotated when you go to different frame, at least if the frames do not move with respect to each other.
Oh, okay.
That's why we need that moving information from the beginning. Yes. So what should be, or what can be done here instead, is to only take the linear part, so the rotational part of that isometry, and apply that to the vector. This works and everything's fine. Or you can also transform a displacement vector by multiplying with a linear part, because the displacement also does not change its length if you go to a different frame. It's still the same displacement, same length, just a different coordinate frame representation so you change the numbers, but the length stays identical.
What do you mean by the linear part? You can separate the transformation into...
The question was, what do I mean with the linear part? This is sort of taken from the eigeninterface. So the linear part, as its rotation plus translation, the linear part is usually the rotation is usually referred to as the linear part. Yeah.
So the library is already assuming some certain nature of the frame of reference, like you're doing Galilean transformations always, and not, let's say,
yeah, the comment was that I'm assuming that it's like a certain kind of transformation. Yes, so I'm assuming this rotation and translation part. I also have scaling, rotation, and translation, which would more be an affine transformation, but I'm not trying to model anything else yet. Yeah. Good. Now we had that earlier. It's also possible to declare user-defined index structs. This can be done like this here. So we derive from a non-Cartesian index type. Maybe we want to represent the slope and offset of a line fit and put that in a vector. Then you could create these indices and again use them in a vector. So the major difference between Cartesian and non-Cartesian indices are that certain operations are only allowed for Cartesian vectors. For example, transforming to a different frame, taking the norm, the cross product, the dot product, that's only valid in a proper vector space, which means it's forbidden for these non-Cartesian index types. Good. Now I want to move on back to the slogan from the beginning. If it compiles, it works. So far, we've mainly applied that to the physical and mathematical part of the problem space. But of course, you can also have problems or bugs that arise when you, like from the C++ implementation part of your library. A question regarding that, again for the audience, what are the most common bugs that you can think of when using a C++ linear algebra library? Does anyone have an idea what the bugs could be?
User error of the data going in?
User error of the data going in, yes, of course. You can. That's also the thing that remains even with my library. Of course, if you input incorrect numeric values, then yeah, you're lost. Maybe if I specialize the question a little bit, if we have an expression template-based library, if we think of ranges with the borrowed ranges, does anybody have an idea what could be the problem?
Dangling references.
Dangling references, exactly. That's the first problem. And the second problem with a linear algebra library that might occur, if you think about assignments, left-hand side.
I would say that's not the defect of linear algebra, it's the defect of the template expressions.
Yeah, the comment was that it's the effect of template expressions, but of course, yeah.
Which is not necessarily the same thing as linear algebra.
Yeah. Yeah, the second, so anybody have an idea about the second problem that can occur?
Size mismatches?
Size mismatches, yes, of course, but I'm preventing these.
Okay.
So it's aliasing. So if the left-hand side and right-hand side aliases, so if the types are used on both sides, then you can run into problems. And we will see how this can all be prevented. First of all, I want to start up with expression templates and order variables. So as an example, let's assume we have a method calculate offset that returns an eigenvector 3D by value. Furthermore, we have a pre-existing vector A that we've initialized with some values. Now we can write a code line like this. We add vector A to the result of calculate offset. We calculate the norm of that result and assign it to a double. Everything's perfectly fine here. This works. But we can change one small thing that makes this break down. And this is if we capture the result of the addition here with an order variable and calculate the norm in the line after. Anybody has an idea what happens here? Or what is the problem? What is, or does somebody know what the type of that sum variable is? Yeah.
Some has a reference.
Yeah, it's the expression template. So we're capturing, or somehow hidden, we're capturing the expression template that describes how the addition can be calculated. At least that's the case for most linear algebra libraries, because they don't execute eagerly. They simply return an expression object that describes how this can be calculated. And now, as I mentioned earlier, calculate offset returns by value. And usually when you have large data types like vectors and matrices that are stored in a matrix expression template, you store them by reference to be efficient. Meaning we're storing a reference to a temporary that's no longer valid on the next line, and bam, your program crashes if you're lucky, or it silently works and crashes at some later point when you change something. The same thing would also happen if you capture that sum variable by reference. then exactly the same situation. Now, the question is, how can we prevent this? So maybe we could think of something like prevent the creation of matrix expressions, but yeah, that's not directly possible because it's needed for the implementation of the library, of all linear algebra libraries. But what we can do instead, we can prevent all calls of methods on L-value matrix expressions. This is something that is possible, and I will show on the next slide how this can be achieved. Brief break. So this is again the example of the addition operator that I showed earlier. We now need two versions of that addition operator, one that is L-value reference qualified and one that is R-value reference qualified. Meaning for an L-value we pick the first one, for an R-value we pick the second one. And now in the L-value reference qualified version we can simply check whether this is an or whether we are in a matrix expression, and if this is the case, we fire a static assertion because we're in an L-value matrix expression calling a method on it, and this is exactly when the problem occurred in on the previous slide. I should mention that this here, of course, has to be done for all methods. So in the previous slide, the problem occurred for the norm method. Here I'm showing the addition operator, so not to confuse the two. Then, of course, an addition has a second argument, so that other argument we're using here, and we also have to verify that this is not an L-value matrix expression, which is done with a helper method here. If this is an L-value matrix expression, we get a static assertion, as always. Now, the actual implementation of that addition method is, as I mentioned, just the addition of the two underlying types. What is important to note here, in the second example, the R-value reference qualified version, we have to do a std move on the this pointer to end up in the R-value reference qualified version of any method that we're calling. Otherwise, we would just end up in the L-value reference qualified version. So again, this is a nice example of our slogan from the beginning. If it compiles, it works.
So you
Question?
rely on eigen doing the right thing as well. So you're basically forwarding the feature to eigen. No?
The question was whether I'm relying on eigen doing the right thing. No, I'm just forwarding to eigen to do the runtime computation. So this will return an eigen expression that I'm later using to calculate the result at runtime. But this has nothing to do with the checks for the L-value matrix expression thing that I'm doing.
That means that eigen has to do something similar.
No, not necessarily, because eigen is the eigen expressions. The question was whether eigen has to do something similar. No, because I'm always wrapping the eigen types inside my library. Of course, if the user, I have methods to access the underlying, the unchecked const matrix and mutable matrix are the names, to access the underlying eigen types, then all bets are off. The user can do whatever he likes, and this problem can occur. But as long as you stick with the library interface, this can no longer happen. Good. If you follow the standard pretty closely, you might have read that using this is coming to C++23, as far as I understood. This would simplify the solution, meaning I only have to write the method once. So I can use this explicit, what is called explicit self-argument, the explicit object parameter, thanks Ben, with this keyword, and then the usual template deduction rules apply, and I can do a perfect forwarding of that argument and do the checks just once. So looking really forward to that. That would be really helpful for my library. Good. Now moving on to the second example where we had problems. That was aliasing. So here, this is eigencode again. So we're accessing a block on the right-hand side of that equation from an eigenmatrix, a 2x2 block that's shown in orange here. And we're assigning that to another 2x2 block that's shown in blue here. Now what's important to notice here is that the two blocks overlap. So this element here, shown in red, is actually part of both blocks. And this means when we start the assignment that the 3.1 from the top left would override the 2.4. And then when we come to the assignment of the bottom rightmost element, the 8.5, then this red element has already been overwritten with a 3.1, and we have the aliasing problem. This would lead to an incorrect result. Now, again, a question, what do you think? Can this happen with typesafe matrix? Is this still possible? Ben thinks yes.
Types and indices.
Sorry, what was it?
The types and indices match.
If the comment was if the types and indices match, yeah, but they cannot match in this case because they have to be unique. So the rows and column indices are unique. You can't have repeating indices, meaning this case at least is no longer possible because the two blocks have different indices. They describe different things. You cannot assign them. This is invalid.
If they were of the same types, you would actually be allowed to assign a small matrix into the middle of a larger matrix if they align?
Yeah, the comment was if the types match up, you would be able to assign a small matrix into a bigger matrix. Yes, of course, this is possible.
That's an operation that you
Yeah, a block operation. Yeah, you can simply, yeah, just like with any linear algebra library, just assign a subblock. So the subblock that you pass in has to have the correct type, and then that's automatically put in the correct position in your matrix, and you're done. So you don't even have to specify where the block goes. You simply create the block with the correct indices, and then the matrix knows automatically where it belongs, and it still checks that it's a consecutive block of consecutive indices. Otherwise, it would say, okay, this is not what you want to do probably. Then you need that special method we had in the beginning where you can like pick up random indices from your matrix and assign them.
So you're saying it does actually deduce the placement of the submatrix into your larger.
Yes, it does deduce the placement of the submatrix into the larger matrix because it's part of the type. So
Right.
when you
But
call
it would have to be a unique position. It couldn't.
it would have to be a unique position, correct? And as I mentioned, as the row and column indices have to be unique, the position is going to be unique. There's no way you can have a non-unique position, at least I think, if I'm not missing something. Good, now on to the next operation that can be aliasing if we multiply two matrices. So here we have two matrices, Jacobian, and we multiply it with my matrix on the right-hand side, and we assign it to the same matrix, my matrix, on the left-hand side of the equation. What happens here when the first element of the result is calculated is that we take the blue block here, the row, multiply it with a column, and we overwrite the first element in the top left position of the my matrix. Now, if we do the multiplication of the second row with that first column, we already get the new value that has been overwritten, which means we're ending up with incorrect results in the multiplication.
You don't compute a temporary matrix that you put the result into
The
and then assign it?
Comment was whether we compute a temporary matrix and then assign it. You're like sort of one slide ahead. We'll soon see how this can be solved, and yeah, that was a spoiler for the solution. So what do you think? Can this happen with typesafe matrix, that we multiply two matrices and assign it to a matrix that's also used on the right-hand side?
Yeah. No.
It can happen.
The units on my matrix would be different on the left and the right.
So the comment was yes in one comment, and the other, well, no in one comment, and the other one, no.
The result of the J
Yes.
matrix and my matrix would have different
Yeah,
units.
and the answer is it depends. So both of you are right. So it depends. In general, usually you would end up with a different type on the left-hand side. So if you multiply my matrix with a Jacobian, then usually the Jacobian goes to a different vector space and has different indices. And in this case, this can no longer happen. But it could still happen if the Jacobian has identical row and column indices. Then this is still possible. So it can happen, but it's in rare cases. So we still need a protection against this. This can occur. And last operation that can be aliasing, we can take the transpose of a matrix and assign it to the matrix. Again, the question, what do you think? Can this happen with typesafe matrix or not?
If the row and column indices are the same.
The answer was if the row and column indices are the same, yes, and it's even a little bit more if the matrix has the proper type, because usually the transpose of a matrix is a different matrix. Only for Jacobian matrices and information matrices, which are the inverse of covariance matrices, you can do that assignment and run into aliasing. So again, I don't know, 95% of the problem disappear already, but there's still a small part of the problem that's still remaining. Even though it's important to keep in mind that covariance matrices are usually symmetric by design. So if they have the same indices, they are symmetric by design. So the question is whether this is actually a problem. If a covariance is supposed to be symmetric, is it a problem if I put, I mean, you can have the situation that it's not symmetric due to numerical inaccuracies, but then is it actually a problem if I have the numerical inaccuracies transposed? Yeah, it probably depends. So I will show how we can solve the problem, and then, yeah, we can still decide whether it makes sense to do that check or not.
When you generate the units, sorry, I'm thinking only
Yep.
units, but of the matrix of the coefficients, do you keep the order of which is column and which is row? Because if that's the case, then not even if we have the same units, you will have the same units in the transpose positions, right? Because you will have, let's say, dyc, dxc, and the other one would be dxc, dyc. Right? If you keep the
Yeah.
order, right? If you don't collapse into...
Yeah, I'm not sure if I understand anything. Maybe let's take that offline.
Goes
Yeah.
across the diagonal.
Yes, yeah. But they can be distinguished because they could be different types as well, in principle.
Yeah. Okay, let's take that offline maybe. Good, so let's see how we can prevent this. So on the top here, we have an equation. So we're assigning to my covariance, and what we're assigning is my covariance plus my Jacobian multiplied with my covariance multiplied with my Jacobian transpose. And on the bottom here, I've shown the expression tree that is built from that. And now if we want to see if aliasing can occur, we have to take the type of the left-hand side argument, which is the covariance in the orange block here, and run that through the whole expression tree and see if we find the same type underneath a potentially aliasing operation. We will see how this goes. So the addition here is not an aliasing operation, but we still have to check the subtrees underneath that addition. So on the left-hand side, we have a covariance. So this could be aliasing because we have the identical type, but we're not underneath an aliasing operation, meaning this is no aliasing, no problem. And now we'll move on to the right-hand side of that expression tree. So here we encounter a multiplication, which is a potentially aliasing operation, meaning we're marking the subtrees here with red arrows. We again encounter a multiplication in that subtree here. So again, this can be aliasing. And in the last leaf down here, we see, okay, we find the same type, the covariance, that we're also assigning to on the left-hand side, meaning this is an aliasing or can be an aliasing operation. There's still a further condition, of course. You could also use a different variable with the same type. That's possible. Then we would detect an aliasing where no aliasing occurs. But if you want to prevent that, I think the Blaze library does it like that. You could compare like the addresses of the two elements and be 100% sure that it's aliasing. That depends. So next slide, we will see how this is implemented in code, C++ code. So we're going back to the promotion to the addition type we had from the beginning. We now add a method called canAliasWith, and this gets a template argument with which is the type of the left-hand side of our assignment, and it also has a Boolean argument which specifies whether we are inside an aliasing operation or not. Then this method does nothing else than forwarding the call to the two sub-expressions on the left and right-hand side of the addition, calling canAliasWith there, and also forwarding the Boolean argument that we passed. So here, that's fairly simple. For multiplication, it looks almost identical, a little bit different. Because the multiplication is a potentially aliasing operation, we're now forwarding to canAliasWith and pass a Boolean argument of true. So we're saying, okay, you're inside an aliasing operation now. Please check whether the same type, the left-hand side type, occurs in any of these sub-expressions. And the last block that we need, so now we're inside the class Typeset Matrix. There, the actual aliasing check is done. So this is an aliasing operation if we are inside an aliasing operation, so if the Boolean flag is true, that we've got passed down. Furthermore, the matrix scalar type has to be identical. The two row and column index lists have to be a sublist of each other. And the matrix tag type has to be identical. And then this is, or at least has a very high potential of being an aliasing operation. And then the last ingredient that we need, when we assign to that matrix, we have to execute that check. So we're checking whether this operation is aliasing. The first if-const expression is for the case where it's not aliasing. There we simply assign the underlying type to the current matrix or to the member matrix that we have stored. In the second example, that is exactly coming back to Chris's comment earlier. In that case where it's aliasing, we're evaluating into a temporary and then assigning from that temporary to the matrix. And this is sort of solves the problem. In that case, yeah. Again, a nice example, I think, of if it compiles, it works. Good. Now I want to show a brief excerpt from a paper. I'm not sure from which year it is, might be a little bit older. It's called P1417, Historical Lessons for Linear Algebra Library Standardization. And I want to read that quote here because it's fairly important for the talk today. Linear algebra libraries all must figure out what to do if the user attempts to perform operations on objects with incompatible dimensions. This gets more complicated, though, if we generalize compatible dimensions to the mathematical idea of a vector space. Two vectors might have the same dimensions, but it still might not make sense to add them together. For example, I can't add a coordinate in 3D Euclidean space to a quadratic polynomial with real coefficients, just like I can't add meters to seconds. Yeah, and I should mention you also can't add two 3D Euclidean vectors if they are from different spaces. And this might remind you of something. This is exactly what we did for the whole talk. We prevented exactly this situation. So this checks, we've prevented exactly this. I was really surprised when I found the paper because they had like two things that I'm trying to solve with my library. Second quote is, expression templates may hinder the use of order because the type may be some expression type that may hold references to concrete linear algebra objects. Returning the expression may result in dangling references. This is exactly what we've seen before. We've prevented that by preventing calling methods on L-value matrix expressions. So this is also something that we've checked. This problem has been solved with a library. So this already, there's one question before we come to the conclusion.
So what do you prevent is the formation of the expression or the evaluation of the expression?
The question was whether I prevent the formation of the expression or the evaluation. I'm not preventing the creation because that's needed to get the thing working. And the evaluation, well, yeah, I'm sort of preventing the evaluation, so I'm preventing any calls, any methods on that expression. So you can't do, if you just create it, it's still fine. As long as you don't access the dangling references in there, it's fine, throw it away. You can do that.
So but that depends on the expression not being evaluated ever.
Yeah, so that depends on the expression not being evaluated ever. So normally this doesn't happen. So yeah. Another question?
Yeah, so just taking, I guess, a different approach to the expression template, capturing issue. Looking back at Dave Abraham's keynote yesterday morning, if you treat them as true value types that actually do own the underlying content, if there's still some live reference to it, then doesn't that kind of address the?
Yeah, the comment was whether coming from Dave Abraham's keynote earlier, whether if we make them these matrix expressions as true value types so that they store the actual content, if this would solve the problem. Well, the point is this would mean you have to store all the vectors and matrices, which can be fairly large, inside that matrix expression, unless you had another idea. So for efficiency reasons, I would guess that's out of the picture, at least in most cases, but it would solve the problem, but yeah.
Well, but the things you would actually be storing would just be, a reference counted object referring to the actual content. Okay, we could maybe store a reference counted object to the actual content. Maybe that's possible. I would have to think about it. So yeah.
If the expression captures a temporary, it can know that and then own a move.
Right.
For that.
The comment was that the expression could know that it captures a template, temporary, and then make a copy of that. Yeah, that would be possible. But there we again back to one of the design principles that I didn't mention explicitly. I don't want to have things happen under the hood that the user is not aware of. So like taking temporaries. There would be another option. You could actually also in my matrix expression, you could encode the fact that you're storing a reference to a temporary, so that one of the inputs of one of the operations fairly down is a temporary. And then you could do the same expression tree evaluation that I showed for the aliasing case, also in the case with the dangling references. That would be an implementation option. Just last week I thought about that when I prepared the talk.
Yeah.
This is a viable option, I think.
I think the reference counting solution would take more overhead than it was worth. And just as a general umbrella, broad stroke statement, I like mutability consistency. If you're going to do something on the right side, don't mess up what's on the left side.
Yeah, the
you
common.
have to put it into a temporary. I know if it's going to be more expensive is better than wrong.
Yeah, the comment was basically more expensive is better than wrong. Maybe can we hold off the further questions? Yeah. I'm coming to the summary, so we're almost out of time. So let's do the summary, and then we can do the remaining questions. So what have we achieved so far? We've seen that we've achieved full support for physical units in vectors and matrices. Meaning we've also achieved expressive and enforced names for vectors and matrix entrances. So there's no way to access a vector at index 2 unless you circumvent the library interface, of course. We have a protection against out-of-bounds access at compile time, so it's no longer possible to access anything out of bounds. We've come to a proper taxonomy domain model for all linear algebra types, at least all the ones I encountered so far, which is fairly important, I think. And then if we have that, I think that the concepts, if you implemented it with concepts in that case, just fall off the trees. The concepts then are just like a lower level. If you have the full domain taxonomy modeled in your type system, then the concepts can be used for the smaller parts of the solution. We've also achieved a compatibility check for index structs and matrix types for all linear algebra operations, as we've seen. We have a built-in coordinate frame tagging. Yeah. And last but not least, the most important part, my slogan from the beginning, we've come as close as possible to, if it compiles, it works. So this concludes my talk. These are a few references. I mentioned the physical units library. There's an earlier version of my talk. On the bottom right, a little bit after my talk, there's an example from Withopf, how Uber Aurora use the units library. And last but not least, I want to mention that we at Bosch are hiring. So if you're interested in automated driving and joining Bosch, please check out the linked job linkings here. And this concludes my talk. Thank you for listening and looking forward to your questions. I think we have 1 or 2 remaining at least. So thank you. Yep.
Question about reference frames. So you're encoding the reference frame in the type. Right.
Yes, I'm encoding the reference frame in the type.
You have different reference frames, and presumably at some point you want to join them. Right. So does the library know how to transform from one reference frame to the other?
The question was whether the library knows how to transform from one reference frame to the other. No, so the library does not care about the actual content, so the numeric values inside the transformation. This would be the responsibility of some other library. So the user has to specify the values, the numerical values of the transformation, and my library only represents like the syntactic sugar, from which frame to which frame does this go, and is it an isometry or maybe just a rotation? This is what's the main purpose. And yeah, the numeric values, we have other libraries for that, that you could use for that. Any other questions? Yeah.
I was going to save this for if there was nothing else. So I work on a code base that deals with relativistic frame transformations and different coordinate systems that differ by relativistic factors.
Mm-hmm.
Do you think it would be like fundamentally difficult to also support that kind of transformation between coordinate frames?
The question was
Galilean.
Whether this also applies to relativistic frames. To be honest, you would have to explain what these frames are first, but maybe I can answer with a little bit different example. For example, you can have like angular frames. So until now it was Cartesian frames, what I described, but maybe you have a polar frame or something like this. That's currently also not part of the library. This could be done in a similar way. So you have to, well, for the Cartesian ones, you also have to register these indices with the library ones. You could do the same thing with a polar frame and maybe also with a relativistic frame, but I would have to understand first what's being done there. But usually I guess it's possible you could put all the magic in a special type for that. I guess it would be possible.
I'd have to think through whether your isometry operations could be adapted or extended.
Yeah, I'm not sure if the isometry operations could be adapted. This is sort of tailored to that problem of isometry or affine transforms. If you have something different, maybe you need a different interface or something else. Yeah.
Thanks.
True. Any other questions? Doesn't seem to be the case. Then thanks everyone for being here. Thanks for listening.